One clearly very important question is, how do I actually build a trie? Like, what would be the instance variables in Java? So I'm going to give you one possible solution. There's many, but this is the first solution I'm going to run through. I think it's very natural. So it consists ultimately of a tree of nodes. We have a root node, and then that root has some children. And every node in the tree has a character, for example, the letter A, an is key boolean, which indicates if it's blue or white. Basically, is it the last character in a key? And then lastly, maybe a little puzzlingly, a data index character map. What's that? Well, it's a map from character to some value type. In this case, my data index character map will map to node values. So for example, this letter A on the right, it will have 3 children. It has a child if you go to the D child, the mth child, and the pth child. So basically when you're looking at this node, you say, hey, can I get my child corresponding to the letter D? That's what a data index character map was, right? It maps characters to things, in this case, nodes. So that might be a little hard to wrap your mind around, and so in the next slide I'll give you another alternate picture of that. Now before I do that, one thing I want to note is that I've set up here a variable called R that represents how many possible children I have. In this case, 128, and that's because I want to support ASCII. But you could change this if you wanted to support other characters. So now back to the data index character map. So let's consider what A and W, these two nodes, would look like if we did a box and pointer diagram for our data index character map. So here we see our node contains the letter A for our character. It is blue, and it has a next pointer that points to an object that contains links to all my children. So the children in this case that I have, well, I only have one, which is the W character. So this 119 is used because that indicates, since in ASCII W is 119, that's not something I expect you to know, by the way, that means we follow this link and we get to the actual node that contains W. This key is false. It has its own next array, and in this case, it's just a bunch of null links. So that's fundamentally what our trie is with this approach. Now, one thing, actually, sorry, before I get to my other thing, so another cartoon you might imagine is that if I'm using a data indexed character map to represent all of my children, to keep all my children links, what I effectively have is that for each node, there are 128 links drawn here. I mean, it's only a cartoon, so it's only actually 5 lines, but this represents 128 links, and only one of them is used, this W, and all of these others are null. Okay, so an alternate way of looking at a trie is that if I use these specific instance variables, I think this is a more honest picture. We have a root, which has 128 links, only A and S of which are used. Then we have an A node, which has 128 links, only the W link of which is used, and so forth. And so here's just the code again. So maybe pause if you need a chance to just take that in. And so I'm going to make one last change, which will get us to our implementation, which is that I'm going to notice there's some redundancy here. When I follow this A link, I'm always ending up at a node that has the letter A. When I follow this W link, it's always a node that has W on the other end. There's redundancy. So what I could do is remove this character from the node. The nodes don't actually need to store their character because the only way to get to them is along a link with a specific meaning. Okay, so I'm going to get rid of that character. So I'm going to remove that from our representation and things will work just fine. So that's one possible way that we can use a trie, or that we can build a trie. So the last thing I want to talk about in this video is the performance. If this is how we're implementing a trie, where every node has a color and a set of 128 links, what will be the add and the contains runtime? And I want you to give the answer in terms of n, where n is the number of keys. And so for example here, if n is equal to 6, that would be the case where we have A, alls, sam, sab, sad, and same. So n is not the number of nodes, it's the number of keys. So try and figure that out. Okay, so it turns out the correct answer is just constant time. It doesn't matter how many keys you have in a trie. Add and contains will be the same, always. So if I have 100 trillion items in my trie, and I do contains potato. Well, the contains operation, you start at the root, you go to P-O-T-A-T-O. Doesn't matter. You're done. Doesn't matter how much stuff is in the tree or in the trie. It's just those 6 links you look at for contains. And a very similar thing for add. So the runtime is totally independent of the number of keys because of the special structure we've chosen. You can write the runtimes in terms of L, the length of the key. So for example, contains for potato will require 6 examinations. So you could say that add and contains are L time. And here I'm mentioning, I use theta for add and O for L, because for contains you can fall off the tree at the top. So you might not have to actually look at every character. But ultimately, the add and the contains operations, the bottom line is they're constant time, unless you're thinking of L as something that varies. Then I guess you can take into account the length of the key. But we didn't do that before, so I'm not going to for this comparison. So what have we gotten ourselves with this new data structure? So we have a new 4th type of character and map, which uses only strings, and it has runtimes that are constant time with no special caveats, that it's not on average or assuming items are evenly spread. It's just constant. Okay. So that's kind of cool. We got this better performance by taking advantage of our special string nature of our data. Now, things are not all wonderful, which should have maybe started occurring to you when we looked at this diagram. All these nulls seem like maybe kind of a strange feature of our data structure. It's a lot of memory. And in fact, in practice, if you build one of these tries that use a data index character map, it's going to have tons of empty links in practice. So in the next video, we're going to talk about ways we can fix that. But I hope that the main punchline here is very clear, which is that this very basic and simple implementation of a trie has constant time operations. Now this video is a lot to take in, so make sure it makes sense before you proceed. It ultimately is simple, but there's just a lot of pieces of the course you have to hold in your brain at once. Okay, so maybe rewatch before continuing, but hope it made sense.